So now I guess it's time to introduce our panelists. So come on up and let's talk about automation at scale.
Hi, hello. I'm Mark Agosta. I'm currently at Microsoft. I'm working as a data science lead among a small group of PhDs who go out and work with our customers, figuring out what are the tool set, problems, and approaches that we need to get people up using machine learning on the Azure cloud. My background actually goes back in common with several people in this group to Stanford, where I can't really say I did work directly in decision analysis, but I applied it in an AI setting, actually working in robotics at the time. And that is kind of the bookends of a rather nonlinear career.
My name is Chris Farrar. I work in SRE at Google, and SRE is Site Reliability Engineering. I've worked on large-scale machine learning systems at Google the whole time, the past 5 years in my career at Google, and we make these ML systems reliable, scalable, and easy to use. My background is software engineering.
Hi, I'm Wenhao. I think I was also introduced yesterday. I work for Salesforce. I have a background in decision analysis. I was a decision consultant with SDG for some time, so I have a strong appreciation of what we do here and what folks in this room can bring to the table in every decision-making situation. I think the title here is wrong, but whatever, it doesn't matter. It's just a title. So I'm really looking forward to the discussion.
All right, so I want to start us out with a topic that we brought up when we were chatting at breakfast, which is that AI systems, they serve predictions or forecasts, but then there needs to be this additional piece of engineering that moves something in the world and, irrevocably allocates resources based on that forecast. And until that happens, the system is merely providing inspiration. So wanted to talk about the difference between predictions and actions, and also wanted to have you tell me about some dangers that you've seen in how people might misinterpret the predictions and then connect them to actions incorrectly. So maybe Wenhao, you'd like to start us out.
Thank you. Yeah, I think when we first started thinking about this panel, I think one of the things we talked about was what does it mean to automate the decision? And for many folks who work on strategic decision, high-level strategy, long-term impact kind of stuff, automating that process seemed to be almost impossible, which I think there's some truth to it. So I think we went to the notion, maybe we're automating repeated large-scale decision. Okay, so there's one realm there, and then there's also, we can use machine learning algorithms to provide forecasts and predictions. So, and then we can take that as input for decision making. So, which brings me back to the question. I think there's modern day neural nets. They produce probabilities, but that probability is the way they have been used. It's not really in the same way that we have been using probabilities in our community. So what that means is that there are numbers between 0 and 1. They add up to 1, but they don't really necessarily represent real probability. It doesn't represent belief, doesn't really correspond to real-world frequency of events. So when we try to interpret those numbers, we've got to be very careful. There's a recent paper that came out essentially points to the fact that if you take the probability, let's say I say this picture has probability 80% that this picture is a cat, then you would expect that if you show the machine 1,000 pictures, it's going to be right about this thing, and the machine outputs 80% probability, then the machine should be right 80% of the time in an ideal situation where the probabilities are calibrated. But that's not the case. So the probabilities are poorly calibrated, so we shouldn't jump right into say, I have probabilities now. Now let's use that to make decision. So that's one thing I would caution against. Yeah.
Let's kind of just riff on that a little bit. This idea of a calibrated probability. I remember talking to some of our folks who were doing click rates, and I was saying, are your probabilities calibrating? Can you multiply them by a value and take a sum and get an expected value out of it? And I got kind of a disparaging look. Of course we're doing accurate work here. We're doing very accurate work here. We're doing this with neural nets, which is basically kind of, in my view, deer-facing headlights. They really did not understand. I think that sets a high bar for this group to say, well, do you understand what a probability is, really? Do you understand what a calibrated probability is? Do you understand the difference between a subjective probability and a frequency? CEO comes to me and says, yes, you're giving me these probabilities. What's the difference between a probability and a percentage? There's supposed to be a laugh on that line. So we have a responsibility as a group to basically carry the torch here.
So from the infrastructure perspective, the biggest thing I've seen that affects the predictions being made and how they're used to make decisions is the quality of data. So I work with large-scale machine learning systems. They do continuous model training. So there's a steady flow of data coming from around the world. It flows into a data storage system. There are models that were very carefully created, hand-tuned, and validated for quality by data scientists, by modelers, and they had them set perfectly for what they wanted. Well, like the upstream of the data, if there's any disturbance in that data, if there's bias, if a certain type of data gets kind of choked off and isn't flown into the system, it throws the model all out of whack and makes the predictions, and then the end result all wrong. So that's something that we fight with all the time, in our applications.
And what about layers of logic that will then sit between the prediction and the decision? So something that we have at Google that SREs know about is policy layers. So maybe you'd like to tell us a little bit about.
Yeah, absolutely. So these systems are large pipelines, right? There's data flowing in one side, there's models popping out the other side and getting pushed into serving and used for the decision making. So at each step in your pipeline, you have to have very careful checks on data quality, like making sure your data isn't biased. So a good example of that, I was telling the other panelists about this a few weeks ago, is one thing we found was that we have data coming from every continent, and if a trawler is trawling across the Pacific Ocean and they're dragging their anchor, and they hit a fiber line, right? Now all of our data from Asia is now not flowing, right? And that affects all of our models. So making sure that we can detect that before it causes a problem, stop the continuous training, right? And now we have a stationary model in serving, which then we go and we react as SREs. We make sure that we find another flow for that data. We make sure that we repair the system to make sure that the decisions can still be made. So that's at the data input side. Now there's other gates at the like right after training. So a data scientist, a decision professional makes the model, right? They bake all their knowledge into it, like life's great. Now they want to make sure that as that model is being continuously updated, that it still meets this criteria, right? So we do very careful checks on the model quality before we push into serving, right? That's super critical. And if a metric for the model performance does go out of line a little bit, then we get made aware. We can roll the model back, or we can let the scientists know, like, oh, there's something wrong with your model. Like, we don't detect anything upstream, but your model is not behaving as you would like. So please take a look. So that's very careful, or that's very important to us.
I'd like to jump in on the monitoring bit. I think that's something we talked about quite a bit amongst ourselves. I think when you push something in production, one thing about a machine learning system is that you always get surprised by what you see in your data. You always do. I remember one time we see an email address that is literally @, which is not a legitimate email address, but that actually happened. in some situations. So obviously something is wrong, but if your system doesn't handle that well, something bad will happen. So my point is that data always surprises you. So for us, it's important to have a way of monitoring that. Not only the errors, but also just general behavior of your system. So I would say when we build a system, it doesn't matter what it is, for us it's very important to be able to have a way of monitoring what's going on in the system and have a feedback loop so that if something, like you said, it behaves weird, we have a way of troubleshooting that quickly, and we have a way of replicating the error and quickly try to fix it. And this has, to me, like if we're dealing with, depending on the specific use case for the system, if it's something that doesn't really have real business consequences, I think that's one story. But if we're trying to use some kind of output of the algorithm to drive decision making that has real consequences, now we might be in trouble if something goes south. So I think that monitoring, it might not be very intuitive. Like before I even push any system in production, I need to worry about how I monitor it. But to me, like if you do that after the thing is already in production, it's too late. Yeah.
So if I can just throw in a comment there, I think the takeaway here is that the kind of academic model, the academic style of I'll build you a model, I'll deliver the model, you have the model, and good luck, run it. It's been tested. Doesn't work in the wild. That now you, as a provider or as a consultant, you now have a responsibility in terms of model management. That there's an ongoing responsibility that somebody has to take up to manage models. Nothing survives the wild.
So if you guys are using machine learning models in production, do you have heuristics that you fall back to in case there are problems?
Let's go back to the rules that were there before we put the model in.
Yeah.
I don't have experience there.
Okay.
What I can say, though, is we have a lot of experience with, I like the idea of looking at your inputs, looking at, for example, the density, the marginals on all the inputs, and see if they change. And there's some really interesting case studies where we put a model in existence into use, and, well, for example, it was picking up certain triage, medical triage, was used for medical triage, was working well. All of a sudden, it's not working well. What's going on? Well, all of a sudden, it had never been trained on people who were teenagers, and all of a sudden, we're getting data coming in for teenagers. So just looking at the inputs, looking at the marginals or some of the distributions.
So we have a question from the audience also on the topic of looking at inputs, but they'd like to know about how the approach changes between the prototype phase and the production phase. What changes in the checks, and also what are those principles of monitoring?
I'll take a crack. So in prototyping phase, when you are trying to explore the data, I think everything goes in the sense that you do whatever it takes to get a good understanding of your data. It could be just gawking. It could be, well, that's not going to be enough, obviously, but I think plotting some summary statistics always helps. So I love histograms. So, and by the way, when you build these kind of things, they transfer easily into your production environments, so distributions and things like that. So one example I've seen is that if you, for example, in all of your training data, for some reason your model metrics is, I don't want to cite a specific number, but just say 10. It's completely out of, let's say the number is 10. And you see ranges between like 8 and 11. But then all of a sudden in production, you see all kinds of 20 and 30. That's an indication that, so now I'm saying when you monitor, it's any summary statistics you can get your hands on. I think that's a first step I would take. And then there's obviously the user feedback. Like they use it, they see it, and they see some strange behavior, they will come back and provide, this is where it goes wrong. And if you have a feedback mechanism built into your system, it'll make your job much easier when you try to troubleshoot.
Kind of at a conceptual level, this idea of building a model, assuming the data stationary, I think as Bayesians we have to kind of take the high road and say, well, there are Bayesian approaches that can learn incrementally. And we have been champions of Bayesian approaches, and I think it falls on us to explore that area where it's no longer just a model built at a particular time with a particular set of data. It's actually adaptive in use.
Yeah, and there's kind of two considerations here, right? There's somebody prototypes a model off of a stationary set of data. It's working great. But then when they actually use it for making decisions, the data that they're using to make predictions is different, right, than their original data set. And then also, there's the case of like a model that's continuously being refreshed with data. So they train their model off of a stationary set of data. Life's great. They push it into production. Now the data coming in to refresh the model is completely different and biased compared to what they had, right? Like that's.
Chris, the audience has actually asked for you to give a more concrete example of a continuously trained model. So you're talking in the abstract now. Maybe you could describe this with an example.
So imagine you want to predict whether a user will click on something on the internet. That's something that a lot of companies want to do. And like with the time of the day, with the time of the year, people's like inclinations to click on different things change. So you would want to have a model, right, that is changing, right? Because like somebody might click on an ad or a thing in the morning, like differently from what they would in the afternoon, right? So as new data comes in throughout the day on the things that people clicked on, you want to make sure you feed that into your model so that in the next time range, your model knows about that information, right? So that's a good one. So click prediction, is a prime example.
I think there's an interesting new set of, maybe it's a new fad in the machine learning world, but there's a lot of research now on what are called reinforcement learning models. This community, probably the best approach to them is if you've done work in dynamic programming, reinforcement learning is essentially the reinvention of, this is maybe a little rough, but it's the reinvention of dynamic programming in a machine learning framework. It is a method where you are looking explicitly at values and temporality. I think we're going to see some advances in that area that are going to help us in doing adaptive modeling and get us out of just this framework.
Yep. So the DeepMind project AlphaGo is a good example of reinforcement learning.
It's a great poster child for how successful it's been. Yes.
Yeah, and I think they've published some some articles on that online as well. So.
I also think that reinforcement learning is by nature, because we've been talking about some neural nets and prediction models. They by nature don't necessarily make decisions, but reinforcement learning models they by nature they make decisions. So a very natural application is I know that Google uses DeepMind's algorithm to sort of manage some aspects of your data center operation to lower your costs and so forth. So that is by nature a decision-making process. You're making repeated decision at scale, hoping to make improvements so that you can do better. I think to me that's also a very good example of now all of a sudden your algorithm is making decision on your behalf in a way without, like, if the algorithm says I'm going to change the setting by 3%, chances are there's no human intervention before that happens. So the only thing that's full automation, and which is really amazing and efficient and fast. And there's also the fact that you need to over time adapt the algorithm because you cannot train something and then run it for a year without any feedback loop, without ever thinking about whether something has changed.
Well, I brought it up, but just to make the caveats is these are very data-hungry algorithms right now, and using them in the kind of circumstances where we typically work in this area is a real challenge. It's going to be a challenge in the community. They have the advantage of being model-free. That's where their data thirst comes from. if we could build, maybe there's some interesting work in partial model reinforcement learning, kind of bringing it back more toward a modeling exercise. In short, the problems of huge demands for data to train or to operate them, and the fact that you still need the data assurance. If that fiber wire breaks, it's not going to, it's still going to be predicting the wrong stuff. So you still have to know that.
So I want to pull us back a little bit, back to basics. How do you think about which decisions lend themselves well to automation, and which ones are a really bad idea?
So very simply, decisions that, so like it's good to use automation, or it's best to use automation and machine learning to make decisions on things where it's okay to be wrong, right? Because if your decision is like, fly the airplane up or fly the airplane down, right, and you're close to the ground, right, like you can't be wrong for that decision, as an example.
What about cars?
So that's a good point.
So I think that's a really interesting way of making that distinction. To me, I was going to say the consequence by itself is actually, it's really important to think about. I don't think it's like high stake decision cannot be automated or shouldn't. In many cases, for example, we do auto, self-driving car. We do autopilot system even with the airplanes. What's interesting is that recently there's a trend in the community, machine learning research community. People started to talk about decision in the literature, not in our sense particularly, but they started to think, oh, wait a second, if my algorithm says there's no vehicle on my left-hand side, and I was wrong, then it's really bad. So I wouldn't say the first time it didn't happen very often in the past, but recently it has started to happen where people in that community started to realize, okay, things that my algorithms do actually have real-world consequences. So how do I make my algorithm aware of these consequences? And when I prepare these systems, how do I make sure that I take these consequences into account? A very simple example is, many companies now build chatbots, and it's automated agent chatting with a customer, helping with some issues. And for chatbots, sometimes chatbots will understand the customer wrong. That's inevitable. But some mistakes are much worse than the others. For example, if the customer says something and the chatbot didn't understand, for example, I said, could you repeat or could you rephrase? That's not really a big deal. It's a hassle for the user, but no harm is done. But imagine if the chatbot, the customer wanted to, for example, cancel some transaction, but the chatbot undertook it as, okay, 1,000 more orders. That's a real problem. So when we do that, the consequence of mistakes, it matters. So to me, the distinction is whether you have enough data. Well, sorry, I should be careful. Whether the data and the situation allows you to build a system that is good enough to do some automation. It's less about the stake.
Well, we'll get back to your idea of probability. I don't think many people in these prediction problems understand that in the end of the day, there's a decision where you're looking at risk on either side. It's not so much does the automated system see the car on your right? It's if it makes that error with a probability that's much, much less than a human does, maybe you're a lot better off. And I think there's a lot of misunderstanding both in the popular press that, no, these systems are not deterministic. It's always a measure of some alternative probability to some other one. And that a lot of the systems, even if they generate, for example, a confidence interval, are not really giving you a probability, or if they are, they're not giving you a calibrated one on which you can make the basis of a decision. And that's necessary.
Yeah, I think that reminds me of something that I was thinking about earlier. The way, let's take a very simple classification model where you basically give me a bunch of things, I'll tell you which type or class this thing belongs to. And it could be as as simple as cats or no cats, or it could be as as consequential as should I apply emergency braking on my self-driving car? So I think the way after you produce the probability, the last layer is typically a argmax. What that means is really just like, let me look across all the classes and find the class that has the largest number between 0 to 1, and that's the class I'm going to predict. That's one of the reasons why these probabilities are, like, you really shouldn't take them as real probabilities. So the way this, and which also leads me to the thinking that for a long period of time, the community of machine learning, they have been chartered with this task of improving accuracy. There's a reason why we're so obsessed with accuracy, because in many situations, we don't really know the downstream task. We don't really have the luxury of understanding the use case of our algorithm. All we can do is to improve the accuracy to the best we could, so that whoever consumes our services and software and algorithms later don't get, surprised. But that, as we get closer and closer to real world consequential situations, I think maybe that thinking needs to change.
So I'm very excited that you've brought up this direction, because this is going to open several doors that both the questions and I personally want to see discussed. And that is really that connection between the raw outputs of these models and the real-world actions or decisions that come out of them, and how we should think about constructing that leap, and maybe what the role of decision analysts might be in thinking through how these forecasts, predictions, numbers connect to real-world action. And also the second kind of area is directly from, yes, when researchers create the algorithms in the first place, they tend to be creating them in the abstract and on benchmark data sets, and then they have a standard performance metric, and quite often these things have not even much choice of the loss functions built into them, maybe just one, whichever one was working in the lab. But in real life, you need to, as business decision makers, you need to come up with an incentive function, and then you need to kind of coordinate these two functions, the loss function and the incentive function. These are different, and so you also need to think about constructing that value function yourself. So we've got the construction of a value function, and we've got the leap from a forecast to an action. And I'd love to hear your thoughts on sort of both of those directions, because that's also where this community can contribute a lot.
I think, if I could take that, I think there's an intermediate ground here where you have an assisted automation, and I think a lot of initial systems are not going to be fully automated. Well, of course. I think of an example we built where we were trying to exploit some wonderful work by our econometrics group, estimating elasticities, not only among different products, but among complements and among time. We had temporal elasticities, work that involved some advances in causal modeling. We built a set of tools that generated in an automated fashion Excel spreadsheets that we sent to people in the field so they could do promotional pricing estimates. And we were able to give them verifiable estimates of what their revenue expectations would be, given they change a bunch of prices along a range of different products that they had in inventory, what effects a promotion would have on the next day or the next week's sales, and what their profits would be, and how much they would move. And they were happy, but then they come back to us and they say, well, I have to think about a bunch of other less tangible outcomes in terms of reputation. Right? If I start undercutting prices too much, right? This goes back to the discussion yesterday about how you price services. It's very similar to that. I have to think about how much market share I'm buying if I start decreasing prices. Do I want to buy market share at the expense of profit? And those were not explicitly in our model. However, it was at the initial stage useful for them. So the putting a tool in a person's hand that has a partial value estimation in it that your user can then embellish, perhaps even in this case, filling out the rest of the spreadsheet with their estimates of these other intangibles, explaining to people that adding a judgmental value to a estimated value is a valid way of making a decision, and maybe gives you a step up in terms of now how do I go the next step of automation. And I think there's a way forward in evolution that can be targeted towards some eventual full automation, but is valuable in the meantime.
Yeah, that's a good point. I mean, like back in the self-driving car example, like you wouldn't want to hook your model directly up to the steering wheel, right? That would not work well. Here too, like if you're trying to predict or forecast revenues, right? Like that's great, but it needs to have a human involved at some level, or other signals, right, to make a more accurate or more desired outcome.
I'd say, thinking ambitiously, at some point you may not.
At some point we may not.
But,
yeah.
but
Yep.
for the meantime, maybe, in our lifetime,
Yep.
we may.
Yeah, and then like another example is the stock market, right? If you want to build a model that represents the stock market, like there's, and maybe I just don't understand this well enough, but there's too many outside variables affecting the stock market to accurately build a model. If you had all the data available, you could, but there's this too many like outside inputs that makes that model inaccurate.
I also want to, there's a clarification that I need to make just based on some of the questions that I'm seeing here, which has to do with how you would bake in a human element into one of these models. So it serves some prediction, and then there's a layer of logic that takes the action. That layer of logic could say something like, if the probability is too close to 50%, it means the thing has no idea what it's doing, so switch over to manual operation mode. It's that kind of thing. So that's, sorry, just a little clarification to help you understand what the panelists are saying. Now back to, I think, Wenhao, you were going to comment on the previous. All right.
That clarification kind of threw me off.
So if we've lost our train of thought, then maybe I will orient us on the completely other sides. We've been looking at outputs, and we've been looking at also data inputs. What about that first part around the decision to automate in the first place? How do you frame the existence or non-existence of this machine learning model, and how do you frame those various stages? Like, should we take it from prototype to production? Should we keep it online? Those sorts of big decisions.
So very simply, if you don't have enough data, then you can't automate.
I think I've seen a tremendous optimism often in this kind of decision. When these decisions are made, seat of the pants, there's either, maybe there are two things that are the same, tremendous optimism that we can do this immediately, that I can install a new piece of software and in a few months I can have a decision system up and running. Or maybe it's fear. It's like, if I don't get a decision system up and running, in a few months our business is going to be toast. Our example internally, with our sophisticated users and our sophisticated, if I can make that claim, data science team, to take our finance, take our CFO, and take their spreadsheet financial forecasts and move them to the cloud internally, right? We don't have to worry, well, we had to worry about security, but it wasn't as if we were doing third-party security. We had to worry about organizational change, but the organizational change in this case was internal, and we were well primed to automate our internal processes. It was a 3-year process. It was a 3-year process from the time we gave them the first valid forecast that showed them our accuracies were higher, which is what they were looking for in terms of the predictions that we provide to our shareholders, to the time that they had fully automated their forecasts. So there's a time element. I just want to bring up the fact that there's a time element. Do you want to ask a question?
Well, I just was going to add, we had Amy Hood
Yes.
come speak to us.
Yes, cool.
She's the CFO of Microsoft. She talked about the automation they had done. But she said that, look, the system's going to tell you what's going to happen if you don't improve. Like, if you don't take action in your business, here's where you're going to end up. And so that's helpful, but it's also something that as their leadership team sits around and says, okay, do we want that result? What are we going to do now to change it? and then the system has to incorporate all that.
Well, maybe let's take that, this is your role, but
Go ahead.
but that question, just push it out once and just say that if you're going to make that, if you're going to analyze that decision to automate, is that the temporal aspect is something that is often overlooked.
I think that's in an ideal situation. I think folks in this room and people with this kind of background should be first and foremost advising what kind of things you want to automate in your organization. I think that's because this community brings to this focus on value, what's important, and we know what kind of sort of variables are uncertain and they're data poor. So like we have that notion to begin with, and then when it comes to there are some components of the work or maybe pieces of our decision-making process we want to automate. That's I think. Sometimes I know we talked about AI, machine learning, and data a lot, but sometimes it's not a machine learning problem. It's a can I automate some calculation? It's simple as that. It's not really a matter of model training, and I think all of that should be can be advised by this community. And then when it comes to actually building these systems, I think it's also important to have the sort of the notion why you're doing that, because information is only one part of decision making. In any organization, I think all the information, at the end of the day, you need to take action on that. So wouldn't it be better if people who are going to make that decision, I really like what Thomas said yesterday. Like I think he mentioned something like, as a decision maker, you need to tell your people what kind of information you need for you to make a decision. So I think that transfers to decision analysts. Like if you can tell people who are going to be in charge of automating some of your systems, some of your decision-making components, what would be helpful, I think that in and of itself is something we can easily bring to the table.
But time and time again, though, I've had people come to me and say, I have a great thing. I'm going to automate it. There's this decision that's going to be automated is going to reduce this by that much and cause all these awesome things. I'm like, great, let's do it. I'm like, so where's your data at? Oh, well, like we have 1,000 samples. It's fine. I'm like, no, it's not going to work. I'm like, so how are you get how are you going to get more data, and how are you going to label it? We're going to start building that next, probably next quarter. Like you're probably about 2 years out from having an automated decision, because that is the most complicated part from my experience.
I really like that example because machine learning is typically data poor, data hungry. So I think it's really hard to start from zero system, zero software, zero automation, to say, tomorrow I'm going to start a machine learning project to automate something. I think it's much easier to have a system. It could be as simple as a database in place to get that data over time, to make it easy for people to label it for you. And over time, you would realize, okay, now I think I have enough experience working with the database and enough data. So maybe now it's time for me to try to train a model on that. And by the way, at this point, you probably also have a feedback mechanism already built into the system, hopefully, so you don't have to worry about many other things that involve in this process. So my point is that if you start from scratch, it's 2 years. It's sometimes a very generous estimation.
So I feel like I have to play devil's advocate here. As I have to be the grumpy statistician, right? And I'm wearing my statistician's shirt. So statisticians love to say, hey, don't be trying to dive in after you've already collected the data, right? After you've already got the data and you haven't actually influenced its collection intelligently, then you're just going to do an autopsy of what the thing died of, to paraphrase Fisher. So you've made it sound like not having the data and not even design the data engineering is a problem. And one might argue, on the other hand, maybe jumping in with a blank slate is actually cleaner because you can influence a good outcome better.
Yeah, so I don't think... Yeah, so having the data not having the data is a problem, but not being able. But if you're to automate your decisions, right, not having the automation in place to get your data and get your labeled data, I think, is the key problem, right? Like that automation needs to come first if you're going to have an automated decision.
And yet you have to design that automation. And I imagine people in this room also would have something to say about the designing of the automation of data collection, right, and how to do it.
I understand your point. You're saying you're in a much better position if you can design the experiment. True. But the time element and the effort, and automation maybe misses part of the point that often the rub is that you need to get data labeled. If you're doing classification, there's often a intensive manual step to have a cadre of semi-skilled folks go through thousands or millions of cases and actually indicate the true value, the gold standard. And that can be very tedious. And there are some possible ways of automating that, or some areas where you it comes in an automated fashion. In time series, it's just the next time increment, right? You're lucky. You don't need a labeling if you're doing time series. But it's often the rub when you get the data set and it's unlabeled, and then you go back to the client and you say, oh, by the way, I need something I can predict against.
Yeah, like a good example of what you just mentioned with respect to labeling is like if you want to computer generate like a hand, like the computer needs to know what a hand looks like, right? So you need probably millions, if not hundreds of millions of examples of hands, but you have to tell the computer, oh, well, this is a knuckle. So who does that labeling, right? Like that's a huge problem at scale for data input to a system.
I think we're a very decision-oriented group. So, what kind of decision do we get to make given the situation we're in? If you walk into a situation where we don't have a system, we don't have any data, yet someone is asking for some kind of machine learning model, I guess if I were in that situation, maybe I would try to do some kind of bootstrapping, like the best I can do, manually collect data, label them, get something out. With the fact that keep in mind that it's probably not going to work as well as I might hope, simply because the data I gather probably is gathered in an inorganic way, and I haven't seen as many examples. I probably don't know the organization as well as it could have, but keep in mind we keep on iterate and improve that system. So I would make that choice if I walk into a situation where we don't have a system, where we don't have any automation, we don't have any data set. I would probably go that way. But
so, gentlemen, I just want to be respectful of time. There's 90 seconds left, and so I would like you each to use 30 seconds to pick a piece of advice to give this audience when they think about this topic.
I was going to say something. I think a simple word, we claim to be Bayesians. If you're going to look at mixing data that is empirical with belief, we really have to take that seriously. I don't think we're doing a good job of that. Now that we've got data, let's see what the Bayesian contribution can be. It's a technical challenge for this group.
I think my takeaway is just that the data input to your decision is super important. It's, from my perspective, it's the most critical piece. So thinking about that up front, before you even say, like, I want to make a decision in like an automated fashion, you have to think about all of your points around data creation and data curation and data validation.
I think the decision whether to automate something using, doesn't matter whether it's machine learning or just simple program, it's something that I think a decision analyst should really contribute to. I think we're very well positioned to do that. And secondly, if we're automating some system to help us make a decision, we need to make sure we contribute to the conversation so that the system designer, builder understand the consequences of what's going to happen with the system. That's where we come in.
Well, thank you so much. Let's thank our panelists.